Yeah, I want to start again to talk a little bit about what we are doing at Johannes Kepler University in our research lab. So as Daniel already introduced you, we are talking about feature-oriented development, and where feature models are commonly used to represent the commonalities and variabilities of a software product line. But I will focus more on the aspect of product lines where the feature implementation artifacts are split across different artifact types. And for instance, in this pick and place unit example, we have here the feature crane, which can not only be implemented using source code, but also in the feature there could be also components which are for simulation purposes, like here some Java code or something like that, or for instance hardware configuration artifacts, which are all mapped to the same feature. And as you know, over time, a feature model and this implementation evolves, and also new features get added and more source code, and that means also more complexity is added to the whole system and the product line. So for instance, in that example, we start rather small with a small subset of features, but over time new features are added and the complexity of the feature model increases. And the challenge here is keeping the constraints which are already modeled in the feature model consistent with the implementing source code. And so the main challenge here is, have the constraints over time been correctly updated so that the actual implementation still is consistent with the feature model representing it? And also, one question is, how can we support the developer finding inconsistencies to resolve them in further development stages? So for that, we proposed and also implemented an approach where we start with the source code implementing the features in an AST representation, and then we also have feature to code mappings, which means that for each feature we have the mapping to its actual AST nodes implementing the feature. Then we also have a system dependence graph, which encodes all the source code dependencies within the source code, and we combine both of these informations to lift the actual source code dependencies to the feature model. So we have then lines indicating the developer in the feature model there are source code dependencies which you should investigate further. And to allow helping then the developer finding interesting feature dependencies to investigate, we also implemented an end-to-end matrix which encounters all the feature dependencies within features. So for instance, in that example, you have here the feature stamp to the feature crane. There are 2 lines from stamp to crane, and so the developer knows, okay, there are more dependencies in the source code and in the feature model then to visit. And with this information combined, we can also resolve then inconsistencies between the feature model and the source code much more easily. So to give you an idea how our implementation also works. So for the feature code mappings, we are using the variation control system Echo, which automatically creates and also maintains our feature to code mappings. So for instance, we have again here the feature model, which we saw also in the first slide. And we have 2 features, crane and stack cylinder colored. And as you see, we have a source code file which has also crane features, source code lines for the feature crane and also for the stack cylinder in it. And also as a second one, as an example, as you see, all the features can spread across multiple source code files and so on. And with using the variation control system Echo, we can directly map the feature to its implementation. Then secondly, the static analysis using the system dependence graph. The dependency graph encodes all the control and data dependencies within the program. And it enables us to analyze the dependencies using slicing. So we can slice the system dependence graph to just focus on one feature. So how does that come together. We have on the one hand the feature to code mappings, on the other hand we have the system dependence graph, and we traverse the system dependency graph in respect to the feature to code mappings, and when we find a code dependency, so meaning that we cross the borders to a different feature, we have found a code dependency, and then we classify those dependency, and then we can lift it up to the feature model, and depending on the classification, we show it differently in a different color to the developer, so that they know and are aware about that source code dependency. Yeah, as I said, we classify the dependencies because not each dependency is created equal. So we defined different dependencies, but also interactions in the source code to distinguish different impact. So we defined as first a def use dependency, meaning that one feature defines a variable or data object in general, which is used by a second feature. And this has, of course, a major impact in the software system because that can cause compilational errors. And so we suggest also to make it visible to the feature model by either creating a mandatory feature or creating an additional constraint for the different features. Same applies to the call dependency, where one feature defines a method which is used by a second one. Then we come to interactions, which are more behavioral interactions between features, but still are valuable for developers to know because for evolution purposes, it's much easier to investigate them when you know that there are interactions between them. So write-write interactions are two features who write the data object, the same data object which is defined by a third feature, and this could be a conflict. It not has to be, but it could be a conflict in the software system. And so there should be an additional constraint to show this to the developer. And write-read interactions could be on purpose. So one feature reads a variable which another feature reads, and the source variable is actually defined by a third feature. Could be on purpose, but still it should be visible in the feature model that they use each other with a uses constraint or something like that. And third interaction type is a call interaction, which is not that severe like other interactions or dependencies, but these are two features calling the same method of a third feature. And this is good to know for a developer, just to give them then an idea that there is a method which is used on multiple occasions on different features. The same with a read-read interaction with data objects, which are read by different features. And we can possibly ignore that for resolving them as inconsistencies in the feature model. But it's still good to know as a developer that they exist in the source code, and maybe you want to resolve them in the future in evolving the feature model and the source code even further. But you can imagine that, of course, with these definitions as dependencies and interactions, there could be a lot of dependencies within the feature model. So we thought about it further and developed the dependency matrix to give the developer a concise overview of all feature dependencies within the feature model, where it's an end-to-end matrix between features, where the source of the dependency or interaction, so the definition for a data object, for instance, is listed in the row, and the target, so the using of feature, is listed as the column of the matrix. And how much they are depend on each other is encoded in a value to indicate to point out the interesting dependencies within the feature model to the developer. So, for instance, when we look at this small subset of the matrix, you can see that the feature base defines some certain variable which is used by the feature stack input, and so it should be investigated further from the developer if it's a valid one or if it should be evolved in the future. So coming back to the approach, we have now both, we have the feature model with the dependencies in the feature model visible and the dependency matrix pointing us to the stamp and the crane feature. So we can now start with the inspection of these dependencies. And there you can also see a contradiction already, where the stamp needs obviously the crane feature, but the crane feature is an optional one. So that is not ideal in terms of modeling the software in the feature model. So we now can refine the constraint, and in this case we modified the constraint by making the crane feature mandatory and also added a requires constraint to be clear in the future. But yeah, inspection of the dependency has to be done by hand. So we also introduced some tool support. We integrated that into Force, the tool which Daniel is also working on his PhD. So you can see the feature model again with the lines indicating the dependencies and interactions in the feature model, and we have the dependency matrix indicating all the relationships between the features. And yeah, the developer can then identify interesting dependencies using the matrix and then select the dependency to investigate further. And then we can see how the data and the control flow is mapped to the system dependence graph, and can then directly from there see how that interaction is created. And also we can go into the source code and see, okay, there is the variable defined, and here is the usage of the feature crane in this concrete example. So we can not only have to view into all the source code, we can directly point into it. But yeah, coming back to the evolution over time, of course, the features evolve and the feature model evolves. And so we also extended the idea of the matrix not only to show the snapshot of one feature model and one configuration. When we change, we evolve the feature model, 2 new features are added here, and we also implemented the evolution matrix with the same notation, so n by n matrix, to indicate the changes between one version to the next. And when we look again in a subset, there are these 2 new features use other features as well, but one or two of them much more heavily than others. And this should help the developer to investigate, especially those dependencies and detections, much quicker than maybe unnecessary or unintentionally introduced ones. But yeah, for the evaluation of the lifting approach, we investigated in our paper 3 different research questions. Firstly, the utility. So the question was here, can we actually lift complex code dependencies to the feature model, and that correctly, of course. Then secondly, the performance. Does the dependency analysis scale over for an industry-sized project? And also the quality of suggestions, so the suggestions meaning the resolution of inconsistencies. So does the dependency analysis point us to correct relationships between the features, and further do the suggested resolutions are modifying the feature model correctly so that the actual code is reflected? So how did we do our evaluation? So the method, we selected the pick and place unit system as a case study system, and we extended the pick and place unit system for a more detailed analysis of the feature to code mappings, so that we could understand, okay, which features are actually really implemented by which code. I would like to point out that the actual implementation was implemented by a colleague from us, but is not the author of the paper. Yeah, we then automated the replay of the evolution history, which we created, and then we performed the feature dependency analysis. During that, we also measured the time and the performance, how much time it took. And also then we validated all the dependencies and interactions found using the manual code inspection. So we dived into the dependencies and interactions and validated them by hand. And then we used the dependency evolution analysis, so the matrix, to find out, okay, how does the changes are reflected over time? And are dependencies which we found earlier are resolved, or are they still persistent in the next version? Good. Then coming to the results, to research question 1 utility, we had 16 different versions from 2 to 24 features. And we found between 0 for the first version to up to 545 dependencies and interactions for these different versions. We used, as I said, manual code inspection to verify the found dependencies and interactions. So as you see in the graph, you see over time the different versions and how many dependencies and interactions we found. And in the first few versions, not so many of dependencies and interactions were found, which we based on that their core components were added over time, and at some point new features were added which used much more status variables to check certain states of these main components of the pick and place unit. And so we found that this dependencies found are correct, and we could verify them using manual code inspection. Then performance, we performed using the replay 20 runs of our analysis. We omitted the first 5 runs due to warm-up of the virtual machine. And that's the results. As you see, again, there's different versions and the execution time. Most of the time is spent in establishing the feature-to-code mapping, so retrieving the code mappings from the different AST nodes from the echo variation control system. Secondly, then the system dependency graph, weighting it, and the actual feature dependency analysis was a smaller part of the overall runtime. So, of course, as expected, the time increased over time with more features, more source code, but it still showed us as important points where we could already increase again so improve our algorithms to improve the computation time even further. Then third research question, qualitative suggestions. So from the different dependencies found, we derived suggestions, and we compared them to the manually derived and created dependencies between features. And we used also the evolution dependency matrix to rank those suggestions, meaning that we first looked at the features relations with the higher numbers than others. So again, when we look at the same example as before, we again see here the difference between having a huge impact from one version to another. And so all of these 4 indicated dependencies were verified by manual code inspection. So the analysis pointed us to those feature relations, and we could verify those relations using the manual code inspection. And the additional constraints we added then showed were correct. And also we found for different versions, of course we did that for all of our versions, but this is only a small example to give you an idea how we did it. We found similar results for all of our versions. Of course, that is not only, that's part of our paper, but it's still ongoing research, and currently we are conducting an industry case study with our industry partner, Keba, and there we are currently investigating the analysis with feature with 40 features and over 100,000 lines of code. The dependency analysis took about 11 minutes. which is acceptable for our industry partner. And yeah, currently we are investigating the found dependencies and interactions, but so it's still ongoing. But the first results we have look really promising, and we are going into the right direction. Yeah, to sum up our work, our approach focuses on lifting source code dependencies to the feature model so that we can then support the developers finding inconsistencies between the actual source code implementing the system to the feature model modeling it. And and we demonstrated also the scalability of our approach using the case study system, but also now with our industry project, which we analyze. We are satisfied for the purpose of having a good analysis result. So thank you very much for your attention, and I'm welcome you for questions.
The node of your feature model corresponds to features in the code, to method in the code, or the granularity is even better.
Sorry.
The node of your feature model represents names of method in the at the code level, or if the granularity is even large.
Currently, our feature to code mappings are on source code line level, so on a source code line level. Daniel, you may want to help me there, but I think that the echo could be even better. But currently, the implementation.
We're reducing it to statement level, so we have a granularity of a statement level, but we could even go further down to each literal.
So because the statement, I understood that the statement level is used for defining the constraints, for relieving the dependencies.
Yeah.
But the dependency is between line of code and not between methods.
For the call dependency, we have a point to the definition of the method, so the actual definition to the actual usage in the other feature. So when we analyze then the definition in our tool environment, we start with the definition and can go to the actual usage in the second feature. So we can find the definition with all the part of the dependency, all the method source code, and then the actual call in the second feature.
That means that in the feature models, you may have not only name of method, but something more smaller?
Yeah, so a feature could be a number of statements in different artifacts. So it could be just variables over different variable pool files, or even just one statement which was added because this feature came up.
Yeah. So the one feature line can also map multiple other dependencies as well. It's just one line to make it more, Don't confuse the developer with 20 lines of the same type. Yeah.
One question. So, if I understood correctly, you talked about constraining the feature model more.
Mm-hmm.
Did you think the way around, so relaxing constraints of the feature model? Because what we encountered with at least 2 industry partners, they have massively over-constrained their feature model, and so they lost variance, which very good.
So this work focuses on really resolving inconsistencies between the feature model and the actual source code. So right now we are really focusing on constraining the feature model more. But we also thought about it already that we can with using also the obvious definitions and diffuse dependencies between, like you see here, this diffuse dependency is kind of obvious for a feature model. So when we are thinking of relaxing it as well, but that's right now future work. And
we actually can do it if you just look at these constraints we are recommending. But in the dependency matrix, it would be hard to find if there are constraints we could remove because there are actually no dependencies found. But if you look at the feature model level and you have highlighted these constraints there, you could actually already make this decision of changing a mandatory feature to an optional because there is no diffuse dependency matrix.
Thanks for your talk. I was wondering, it was not clear to me how did you determine the weighting factors?
Okay.
That at the end get this reddish part from the green and.
So weighting factors, we have written that down also in the paper. That we investigated the impact of the different dependencies and interaction types, and we wanted to show, okay, def use and call dependencies has a much severe impact than call interaction, for instance. So we defined those dependency, these weights, where we commuted these values from by hand and experimented a little bit. But as we stated also in the paper, it would be much future work of us to experiment a little bit further with these weighting factors. And one idea we also have is to let these weighting factors decide by the developers, because in certain domains and certain application purposes, other different dependencies and interaction types are much more severe than others. So the idea is that the developers weights them on his own and can decide, okay, how much the impact should be for computing the matrix.
And would this be related to the fact that when you analyze the evolution, at some point there was some peak because there were some new features, so that will be related. At that point you could ask the question because it would be more relevant to ask at that point, right?
Yes. Yeah. So the idea is that of course the numbers would not change in terms of numbers of dependencies and interactions found, but the impact in that evolution matrix, so where we point the developers to investigate relationships between features, would change so that they can really focus on what is important for them.
Great, thank you.
In your case study, is it possible to, and I think it's better, how does it cost to execute the configuration?
I'm not sure if I understood your question correctly. So we replayed the dependency, the case study system automatically, and creating the case study system. I have no idea how much time it takes by heart right now. I can look that up and come up to you during the dinner.
Maybe the simple question is, can you configure your feature model, click a button, and see whether it's compiling, building, passing the test suite,
you mean
if you just create one concrete problem?
Okay.
Well, it very much depends on the use case. In our case, we are generating specific code from this company, IEC code, that needs to be imported and recompiled and such things. So this takes quite long, but not on our side, but they're on the tool side, basically. So the analyze itself is just a few minutes, but to generate the source code is also just like 30 seconds. And then it takes about 30 minutes until the tool chain of our industry partner did all the import and code generation it requires.
Okay. Because my point is that it could be another way to test whether dependency is missing. Because if you test some configuration that are contradictory to
I don't know. So you might want to, if you are interested in creating multiple configurations and
or use
check
more,
for dependencies.
dynamic execution to see what's going on and to get the truth, because no one gets the truth. The developers have some intuition.
Yeah, the actual idea it is that you start with development of at point 0, and the entire system is growing with this entire toolchain in background. So every time you create a new feature and commit its code, the dependency analysis runs. So in the end, you have to catch up every possible creation because you're just creating it. Basically. Yeah. So afterwards, recovering from existing configurations is a bit more harder because you need to first have this product configured and then analyzed with the dependency analysis to actually find dependencies, of course.
It's great to see such a lively exchange. So that is, of course, the kind of outcome that we want. Feel free to discuss later on. So with that, I would like to close